What is reality made of? Pick up the nearest object to you. Go on. Whatever is within arm's reach right now. A coffee mug, perhaps, a phone, a pen, the arm of the chair you're sitting in. Hold it in your hand. Feel its weight. Tap it with your finger. It is solid, unambiguous, completely, reassuringly real. You can see it. You can feel it. If you dropped it on your foot, you would have no philosophical doubts whatsoever about whether it existed. Now consider this. The object in your hand is made of molecules. Those molecules are made of atoms. The atoms are made of a nucleus. Protons and neutrons packed together at the center, surrounded by a cloud of electrons. The nucleus is made of quarks, and the quarks and the electrons and every other fundamental particle that makes up everything you have ever touched, tasted, seen, or smelled. They are not, as far as we can tell, made of anything at all. They are not tiny marbles. They are not miniature versions of the objects you encounter in everyday life. They are not little balls of matter sitting in space. They are, according to our best and most thoroughly tested theory of physics, excitations in quantum fields that stretch across the entire universe. Disturbances in a vast, invisible fabric from which everything in existence is woven. And it gets stranger. Those quantum fields and the particles they produce and the forces that act between them, they do not, on their own, give rise to the solid, tangible, unambiguous reality you experience when you hold that coffee mug. The solidity, the weight, the color, the warmth. None of that is simply sitting there in the object, waiting to be perceived. It emerges from a collaboration between the object and you, between the universe and the act of observation, between whatever is out there and whatever it is that we are doing when we look. The question of what reality is made of is therefore not only a question about physics. It is a question about the relationship between the physical world and the minds that observe it, between the map and the territory, between the equations and the experience. It is one of the oldest questions in human thought. It is also one of the most urgent questions in modern science. And the deeper we dig, the further down we go, through molecules to atoms to quarks to quantum fields to the very fabric of space and time itself, the more we find that the ground beneath us is not solid at all. It shimmers, it flickers, it refuses to sit still. Welcome to the search for the bedrock of reality. The first diggers. The idea that the world, for all its surface variety, is made of a small number of simpler constituents, is old enough to predate writing. But it was the ancient Greeks who first turned it into something resembling a systematic inquiry. Around the 5th century BCE, a philosopher named Leucippus and his student Democritus proposed an idea of breathtaking boldness. Everything in the universe, they argued, is made of tiny, indivisible particles moving through empty space. They called these particles atomos, meaning uncuttable, indivisible, the smallest possible thing. The rest, all the textures and colors and temperatures and flavors of the world, arises from the different sizes, shapes, and arrangements of these atoms. A hard substance is made of atoms with interlocking hooks. A fluid substance is made of smooth, round atoms that slide easily past one another. The world's endless diversity is nothing but atoms and void. This was not a scientific theory in the modern sense. Democritus had no experiments to offer, no measurements, no predictions that could be tested and falsified. It was a philosophical conjecture, an act of intellectual daring. and for 2,000 years it sat largely dormant while other ideas, particularly the rival theory that everything is made of earth, water, fire, and air, dominated Western thought. Then, in the early 19th century, an English schoolteacher named John Dalton began weighing chemicals. Dalton was a meticulous experimenter with an unusual gift for seeing patterns in numbers. He noticed that when chemical elements combine to form compounds, they always do so in fixed and simple ratios by weight. Hydrogen and oxygen make water in a ratio of approximately 1:8. Carbon and oxygen make carbon dioxide in fixed proportions. The ratios are not arbitrary or continuous. They are always simple whole numbers, as if the elements come in discrete, countable lumps. Dalton concluded that they do. He revived the atomic theory, gave it quantitative teeth, and transformed it from philosophy into chemistry. Each element, he proposed, is made of its own distinctive kind of atom. Atoms of different elements combine in small whole number ratios to make compounds. The weights of atoms differ from one element to the next, and those differences produce the fixed ratios Dalton had measured. For the first time, the ancient conjecture had evidence behind it. Over the following century, the evidence accumulated rapidly. Chemists identified more and more elements, mapped their properties, and began to notice patterns. In 1869, a Russian chemist named Dmitry Mendeleev arranged the known elements in order of their atomic weights and found, to his astonishment, that their chemical properties repeated in a regular, periodic pattern. Every eighth element or so, the properties seemed to recycle. He arranged them into rows and columns, the periodic table, and found gaps, places where the pattern demanded an element that had not yet been discovered. He predicted 3 missing elements in detail based solely on their position in the table. All 3 were found within 15 years. The atomic theory was no longer just plausible. It was overwhelmingly supported, but Dalton's atoms, indivisible, featureless, eternal, turned out to be not quite the end of the story. Cracking the atom. In 1897, a British physicist named J.J. Thomson was experimenting with cathode rays, beams of something mysterious that appeared when electricity was passed through near vacuum glass tubes. The rays traveled from one electrode to another. They cast shadows. They could be deflected by magnetic fields. Thomson showed that these rays were made of particles, tiny, negatively charged fragments of matter. And here was the astonishing part. These particles were the same regardless of what metal the electrodes were made of or what gas remained in the tube. Whatever these particles were, they seemed to be universal constituents of matter. Thomson had discovered something inside the atom. He had found the electron. The atom, it turned out, was not indivisible after all. It had interior structure. It had parts. The immediate puzzle was what the rest of the atom looked like. If electrons were inside it, and electrons were negatively charged, and atoms were electrically neutral overall, then somewhere inside the atom there had to be a positive charge to balance the negative. But where? Thomson himself imagined a kind of pudding, a diffuse blob of positive charge with electrons embedded in it like raisins. It became known, with more affection than reverence, as the plum pudding model. It lasted about 12 years. In 1909, a young physicist named Hans Geiger and an undergraduate named Ernest Marsden working under the supervision of Ernest Rutherford at the University of Manchester, fired a beam of positively charged particles at a thin sheet of gold foil and measured where they went. Most passed straight through. A small fraction were deflected at large angles. A very few bounced almost directly backward. Rutherford described his astonishment memorably. "It was," he said, "as if you had fired artillery shells at tissue paper, and they had come back and hit you in the face." The plum pudding model could not explain this. A diffuse blob of positive charge would gently deflect the particles, not send them spinning back the way they came. The only explanation was that the positive charge in the atom was not spread out at all. It was concentrated in an incredibly small, incredibly dense region at the center, the nucleus. The atom was, by volume, almost entirely empty. If the nucleus of a hydrogen atom were the size of a golf ball sitting at the center of a football stadium, the electron would be orbiting somewhere in the upper tiers of the stands. Everything in between, the vast interior of the atom, would be vacuum. Nothing. The solid world was not solid. It was almost entirely empty space. This remains one of the most vertiginous results in the history of physics. The coffee mug in your hand is mostly nothing. The atoms that make it up are themselves mostly empty, with electrons orbiting tiny, remote nuclei like lonely planets around distant suns. The reason the mug feels solid is not that its constituent particles are packed tightly together. It is that the electromagnetic forces between those particles prevent your hand from passing through. The solidity is a force, not a fact. The hardness is an interaction, not a substance. But even this was not the bottom. Inside the nucleus, by the 1930s, physicists had established that atomic nuclei themselves had internal structure. They were built from two types of particle: protons, which carried positive electric charge, and neutrons, which were electrically neutral. These two particles were collectively called nucleons, and they were bound together by a new and previously unknown force, the strong nuclear force. That was immensely powerful at very short distances, and utterly negligible at the scales of everyday life. This was the world as physics understood it through the middle of the 20th century. Matter was made of atoms. Atoms were made of electrons orbiting nuclei. Nuclei were made of protons and neutrons. 3 types of particle, 2 types of force, and you could, in principle, build everything. It was tidy, it was satisfying, it was wrong, in the sense that it was incomplete. When physicists began building increasingly powerful particle accelerators, machines that slam particles together at tremendous speeds and examine what comes out, they found a zoo of new particles: pions, kaons, lambdas, sigmas, omegas. By the 1960s, the particle zoo had grown so crowded and chaotic that the situation felt less like a theory of fundamental physics and more like a poorly organized stamp collection. Nobody believed that all of these particles were truly fundamental. There had to be something simpler underneath. In 1964, the American physicist Murray Gell-Mann and, independently, the physicist George Zweig proposed an answer. Protons and neutrons, they suggested, are not fundamental particles at all. They are composite objects made of smaller constituents that Gell-Mann called quarks, a name he borrowed with characteristic eccentricity from a line in James Joyce's Finnegan's Wake. 3 quarks make a proton. 3 quarks, in a different combination, make a neutron. The entire particle zoo could be understood as different configurations of quarks, bound together by a force carried by particles called gluons. The idea was initially greeted with skepticism. Quarks had some peculiar properties that made them hard to take seriously. Most notably, they carried fractional electric charges, 1/3 or 2/3 of the charge on an electron, which had never been observed. But by the early 1970s, experiments at the Stanford Linear Accelerator Center had confirmed that protons had internal structure. There was something inside them. Small, hard, point-like objects that scattered electrons at large angles, just as Rutherford's nucleus had scattered alpha particles 6 decades earlier. The quarks were real. Today we know of 6 varieties of quark: up, down, strange, charm, bottom, and top, together with 6 varieties of lepton, of which the electron is the most familiar. These 12 fundamental matter particles, together with the particles that carry the 4 known forces, make up the standard model of particle physics, the most precisely tested theory in the history of science, accounting for the behavior of matter and energy across an enormous range of scales and conditions. The Standard Model is an extraordinary achievement. It is also, almost certainly, incomplete. The quantum revolution. To understand why, to understand what the Standard Model actually tells us about the nature of reality, we need to take a detour into the most conceptually radical set of ideas that science has ever produced: quantum mechanics. In the first decades of the 20th century, a series of experiments revealed that the behavior of matter and energy at the smallest scales was profoundly, irreducibly strange. The strangeness was not a matter of complicated detail that would eventually resolve into familiar patterns. It was built-in, fundamental, inescapable. Here is one way to see it. Fire a beam of electrons, one at a time, individually in sequence, at a screen with 2 parallel slits cut in it, and place a detector behind it to record where the electrons land. Common sense says you will get 2 bands of impacts on the detector, one behind each slit. Each electron goes through one slit or the other, lands somewhere behind it, and the combined result is 2 stripes. That is not what happens. What happens is this. After many electrons have been fired, the detector shows not 2 bands, but an interference pattern. A series of alternating bright and dark stripes that is the signature of waves interfering with one another. The pattern looks exactly like what you would get if you sent water waves through 2 slits and watched the resulting ripples overlap, reinforcing in some places and cancelling in others. But electrons are particles. They arrive at the detector one at a time as individual events. How can a single electron interfere with itself? How can it go through both slits simultaneously? If you add a detector to determine which slit each electron goes through, if you watch, the interference pattern disappears. You get the 2 expected bands. The act of observation changes the outcome. This is not a quirk of experimental technique. It is not something that will be fixed by better equipment. It is a fundamental feature of the quantum world. Particles do not have definite positions and momenta until they are measured. Before measurement, they exist in a superposition of possibilities, described by a mathematical object called the wave function, which encodes the probability of finding the particle in each possible state. When a measurement is made, the wave function appears to collapse to a single outcome. The wave function is not a description of our ignorance. It is not that the electron really has a definite position and we just don't know what it is. The electron genuinely has no definite position until it is observed. This was confirmed conclusively and repeatedly through a series of experiments testing what are known as Bell inequalities, culminating in work that earned Alain Aspect, John Clauser, and Anton Zeilinger the 2022 Nobel Prize in Physics. Reality, at its most fundamental level, is irreducibly probabilistic. The universe, at bottom, does not run on certainty. It runs on chance. Einstein hated this. He spent years arguing against it, most famously collaborating with Boris Podolsky and Nathan Rosen on a thought experiment designed to show that quantum mechanics must be incomplete, that there must be hidden variables, deeper facts about the world that quantum mechanics fails to capture. His instinct that God does not play dice turned out to be wrong. The experiments are unambiguous. The dice are real, and they are loaded only by probability. Fields all the way down. But the standard formulation of quantum mechanics, particles with wave functions, probabilities, and collapse, is not actually the deepest level of the description. The deeper level is quantum field theory. The central insight of quantum field theory is this: particles are not the fundamental objects in nature. Fields are. Imagine the universe as pervaded by a set of invisible interlocking fields, one for each type of fundamental particle. There is an electron field stretching across all of space, a quark field, a photon field, a Higgs field. Each of these fields has a value at every point in space and time, and those values are constantly fluctuating, rippling, vibrating. An electron is not a tiny object sitting in the electron field like a marble in a tray. An electron is a localized excitation of the electron field, a ripple, a vibration, a knot of energy temporarily concentrated in one region of the field. When that excitation moves, we say the electron is moving. When it disappears, when an electron is annihilated in a collision with a positron, the excitation of the electron field dies away, and excitations in other fields are created in its place. Every particle in the universe is a ripple in a field. Every interaction between particles is a collision between ripples. Every force, electromagnetism, the weak nuclear force, the strong nuclear force, is mediated by ripples in its own field. When two electrons repel each other, they do so by exchanging ripples in the photon field. The photon, the particle of light, is both the carrier of electromagnetic force and an excitation of the electromagnetic field. This is the framework of the Standard Model, and it works with extraordinary precision. The anomalous magnetic moment of the electron, a measure of how the electron responds to a magnetic field, has been calculated using quantum field theory to 11 decimal places. The experimental measurement agrees to the same precision. This is equivalent to measuring the distance from London to New York and getting the answer right to within the width of a human hair. No other theory in the history of human knowledge has been tested to this level of accuracy. And yet, the Standard Model has holes. Embarrassing, glaring, fundamental holes. It does not include gravity, the force that governs the large-scale structure of the universe, that holds galaxies together and bends the path of light, has no place in the quantum field theory framework. Every attempt to quantize gravity, to write it as an exchange of ripples in a gravitational field, produces equations littered with infinities that cannot be removed. It does not explain dark matter, the invisible substance that accounts for roughly 27% of the universe's total energy content, whose gravitational effects are seen everywhere from the rotation of galaxies to the large-scale structure of the cosmic web, but which has never been directly detected and whose nature remains entirely unknown. It does not explain dark energy, the even more mysterious entity that accounts for roughly 68% of the universe's energy content and is driving the accelerating expansion of space itself. And it does not explain why there is something rather than nothing. Why, in the moments after the Big Bang, matter slightly outnumbered antimatter, so that when the two annihilated each other, a small surplus of matter survived to form everything we see. The Standard Model describes the 5% of the universe that is made of ordinary matter and energy. The other 95%, dark matter, dark energy, and the origin of the matter, antimatter asymmetry, lies entirely outside it. The most successful theory in scientific history does not describe most of reality. The problem of gravity. There are two great theories in modern physics. Quantum field theory, which describes the behavior of matter and energy at small scales with devastating accuracy, and general relativity, which describes the behavior of space, time, and gravity at large scales with equal devastation. Both are extraordinarily successful within their own domains. Both have been tested to extraordinary precision. Both, in any single experiment designed to probe one or the other, give exactly the right answers, and they are mutually incompatible. Not in the casual sense in which two colleagues might disagree about the best route to the office. Incompatible in the deep, structural sense that the mathematical frameworks underlying the two theories are built on assumptions that cannot both be true simultaneously. General relativity describes a smooth, continuous, dynamic space-time. It is a theory of geometry, of curvature and flow, of the continuous fabric of the universe bending and stretching in response to the mass and energy within it. At its heart is the assumption that space-time can be divided arbitrarily, finely, that there is no smallest unit of space or time, that the fabric is seamless. Quantum mechanics, on the other hand, is built on discreteness. It deals in quanta, minimum possible amounts. Energies come in packets. Angular momentum comes in chunks. You cannot have half a quantum. The world at small scales is grainy, not smooth. Put these two theories together and ask what happens at scales where both should apply. The Planck scale, around 10 to the minus 35 meters, smaller than a proton by as many orders of magnitude as a proton is smaller than the solar system, and the equations catch fire. Infinities erupt from the mathematics. Predictions become meaningless. The universe at the Planck scale, the true smallest scale of reality, is beyond the reach of either theory as they stand. This is the central unsolved problem in fundamental physics. Every candidate for a deeper theory, a theory of quantum gravity that would supersede both general relativity and the Standard Model, must somehow reconcile the smooth geometry of space-time with the discrete graininess of the quantum world. Several candidates exist. All are incomplete. None has yet made a prediction that can be tested with current technology. String theory and the landscape. The most famous candidate for a theory of quantum gravity is string theory. Its central idea is simple to state, if enormously difficult to work out in detail. The elementary particles of the Standard Model, quarks, electrons, photons, and the rest, are not point-like objects with no internal structure. They are, each one of them, a tiny vibrating loop of energy, a string. The different particles are different vibrational modes of this string, in the same way that a violin string can vibrate in different modes to produce different notes. An electron is a string vibrating in one particular pattern. A quark is a string vibrating in another. A photon, a particle of light, is a string vibrating in yet another. The properties of each particle, its mass, its charge, its spin, are determined by the vibrational mode of its underlying string. One consequence of this is that string theory automatically includes gravity. Among the vibrational modes of a string is one that behaves exactly like the graviton, the hypothetical particle that would carry the gravitational force in a quantum theory of gravity. String theory did not have to be engineered to include gravity. Gravity emerged from the framework unavoidably. This was, and remains, deeply exciting. The catch, and once again there is a catch, there is always a catch, is that string theory requires more dimensions of space than the three we experience. The mathematics of consistent string theory demands 10 dimensions of space and 1 of time. Some formulations require 11. Where are the extra dimensions? String theorists argue that they are curled up, compacted, rolled into shapes too small to detect with any existing instrument. They are there. They are part of the fabric of reality. But they are hidden at scales far below anything our particle accelerators can probe. The shapes into which these extra dimensions are compacted. Mathematicians call them Calabi-Yau manifolds, after the two mathematicians who first described them, determine the properties of the particles and forces we observe. Different shapes produce different physics. And here is the problem. The number of possible Calabi-Yau shapes is staggeringly large. Estimates suggest something on the order of 10 to the power of 500 different compactifications, each one corresponding to a different universe with different physical laws, different particle masses, different forces. This enormous collection of possible universes is called the string theory landscape, and no one knows how to choose among them. If string theory is correct, there is no unique prediction of what our universe should look like. There is instead a vast menu of possibilities, and we apparently live in one of them. But the theory does not explain which one or why. Critics argue that a theory which cannot make unique predictions is not a scientific theory in any useful sense. Defenders argue that the landscape, combined with the idea of a multiverse in which all possibilities are realized somewhere, actually explains why our universe has the particular properties it does. This debate is ongoing. It is one of the liveliest and most contentious in all of physics. String theory has not been confirmed by experiment. It has not been definitively falsified either. It remains the most extensively developed candidate for a theory of quantum gravity, with thousands of physicists working on it across the world. And yet after more than 50 years of development, it has produced no unambiguous testable prediction that differs from the Standard Model's predictions. Whether this reflects a profound truth about the structure of reality or a decades-long wrong turn is a question that physicists are, to put it charitably, not in agreement about. Loops and spin. Foam string theory is not the only candidate. Loop quantum gravity takes a different approach. Rather than starting with the particles and trying to find a unified description that includes gravity, it starts with gravity, with Einstein's general relativity, and tries to quantize it directly. The central result of loop quantum gravity is that space itself is quantized, not smooth and continuous, as general relativity assumes, but granular, made of discrete, irreducible units called spin networks. The nodes of the spin network represent quanta of volume, and the links between them represent quanta of area. Space, at the Planck scale, is not a fabric but a web, a network, a mesh of finite units, each one the smallest possible piece of space. Time in loop quantum gravity is similarly quantized. The evolution of a spin network from one moment to the next is described by what theorists call a spin foam, a kind of four-dimensional bubble bath of discrete space-time chunks. The picture of reality that emerges from loop quantum gravity is quite unlike the picture that emerges from string theory, or indeed from any classical physics. There is no smooth background stage on which events play out. Space itself is a dynamical, granular, relational structure. It does not exist independently of the matter and energy within it. It is woven from interactions. Loop quantum gravity makes some predictions that differ from classical general relativity, particularly in extreme conditions like the interior of black holes and the very earliest moments of the universe. If, as is expected, future observations of gravitational waves from black hole mergers achieve sufficient precision, or if observations of gamma rays from cosmological distances can constrain the Planck scale structure of space, loop quantum gravity may eventually become testable. For now, it too remains unconfirmed. The information paradox. In 1974, Stephen Hawking made a discovery that troubled him and has troubled physics ever since. Black holes, he showed, are not truly black. By combining the principles of quantum field theory with the curved spacetime of general relativity, Hawking demonstrated that the intense gravitational field at the edge of a black hole, the event horizon, the boundary beyond which nothing can escape, causes pairs of virtual particles to behave in a particular way. One member of each pair falls into the black hole, the other escapes. From a distance, the escaping particles look like radiation, a faint thermal glow emanating from the black hole. This is Hawking radiation. It is one of the most celebrated theoretical predictions in modern physics. Its implication is that black holes are not eternal. They slowly lose mass as they radiate, growing smaller and dimmer over immense time scales, until eventually they evaporate entirely and disappear. And here is where the trouble begins. According to quantum mechanics, information is conserved. The details of any physical process, the precise state of every particle involved, can in principle always be recovered from the final state, even if the process looks irreversible. Drop a book into a fire, and the information in the book is, in principle, encoded in the precise arrangement of smoke and ash and heat, recoverable by a sufficiently powerful observer. But what happens to the information that falls into an evaporating black hole? The Hawking radiation that carries the black hole's mass back into the universe is, in Hawking's original calculation, perfectly thermal. perfectly random, carrying no information about what fell in. If the black hole evaporates completely, the information seems to have been destroyed, gone, not encoded elsewhere, simply deleted from the universe. But this is forbidden by quantum mechanics. It violates a principle called unitarity that is foundational to the entire quantum framework. If the black hole information paradox cannot be resolved, if information really is destroyed by black holes, then either quantum mechanics or general relativity must be wrong in some deep way that we have not yet identified. Hawking himself initially believed information was destroyed. He later changed his mind, conceding in 2004 that black holes must eventually release their information in some form. But the mechanism by which this happens remains one of the deepest unsolved problems in theoretical physics. In 2019, a calculation using a technique called the island formula provided a partial resolution, suggesting that the fine-grained details of what fell into a black hole are indeed encoded in the Hawking radiation in a way that Hawking's original calculation could not detect. But the mechanism is deeply puzzling, and many physicists feel the problem is not fully solved. The information paradox sits at the intersection of quantum mechanics and general relativity, and its eventual resolution, when it comes, is expected to reveal something profound about the nature of space, time, and the fabric of reality at its most fundamental level. The holographic universe. One of the most remarkable ideas to emerge from attempts to understand the information paradox is the holographic principle. The first hints came from Hawking's own work, when he calculated the entropy of a black hole, a measure of how much information is hidden inside it. He found something unexpected. The entropy was not proportional to the volume of the black hole, as you might intuitively expect. It was proportional to the surface area of the event horizon. The amount of information inside the black hole was determined not by how big the black hole was, but by how large its surface was. This is extremely strange. Imagine filling a room with books. The amount of information in the room grows with the room's volume. The more space, the more books you can fit. Hawking's results said that for a black hole, it was as if all the information about the interior was somehow inscribed on the surface, like text printed on the walls. The Argentine physicist Jacob Bekenstein had reached a similar conclusion slightly earlier, and the combined result became known as the Bekenstein-Hawking entropy formula. But it was the Argentinian-American physicist Juan Maldacena who, in 1997, showed that this was not merely a quirk of black holes. Maldacena's discovery, now known as the ADS/CFT correspondence, or more colloquially as the holographic principle, showed that there is a precise mathematical equivalence between a theory of gravity in a certain kind of space and a quantum field theory living on the boundary of that space. The two theories describe the same physics from different perspectives, and crucially, the gravity theory operates in one more dimension than the boundary theory. Everything happening inside a volume of space, including gravity, black holes, strings, all of it, can be completely and precisely described by a theory with no gravity living on the surface enclosing that volume. The implication, taken at face value, is staggering. Our three-dimensional universe, with all its matter and energy and gravity and space-time curvature, might be the projection of a two-dimensional reality on a distant boundary surface. not in the sense of an approximation or an analogy, but precisely, mathematically, completely equivalent. Every event that happens in the bulk of space is encoded in perfect detail on its boundary, the way a three-dimensional hologram is encoded in a two-dimensional interference pattern on a photographic plate. The universe may be a hologram. This is not a fringe idea. Maldaceni's 1997 paper is one of the most cited papers in the history of physics. The ADS/CFT correspondence has been used to solve problems in condensed matter physics, nuclear physics, and quantum information theory. Its mathematical consistency has been verified in thousands of calculations. Whether it describes our actual universe, which has a positive cosmological constant and is not of the specific type that ADS/CFT strictly applies to, remains an open question. Physicists are working to extend the correspondence to more general geometries. The prize, if they succeed, would be an understanding of quantum gravity derived not from the gut of a black hole, but from a two-dimensional quantum theory on the universe's edge. Reality, it seems, may have one fewer dimension than you thought. The measurement problem revisited all of this: quantum fields, strings, spin foam, holograms, still leaves untouched what many physicists consider the deepest problem of all: the measurement problem. The quantum wave function evolves smoothly and continuously according to the Schrödinger equation. It spreads out, develops superpositions, interferes with itself, and then, when a measurement is made, it appears to collapse, abruptly, discontinuously, randomly, to a single definite outcome. But what counts as a measurement? What distinguishes a measurement from any other physical process? What is special about observation? The Schrödinger equation does not contain any special category of event called a measurement. It describes all physical processes uniformly. Why does the wave function behave differently when it is being observed? This is the measurement problem, and it has haunted quantum mechanics since its inception. Several interpretations of quantum mechanics have been proposed, each attempting to resolve or dissolve the problem, and none commanding universal agreement. The Copenhagen interpretation, the oldest and for a long time the most widely taught, draws a sharp distinction between the quantum system being measured and the classical measuring apparatus. The wave function describes the quantum system. The measurement collapses it to a definite outcome. Why this happens is not, in the Copenhagen view, a question physics needs to answer. Shut up and calculate. Many physicists have found this deeply unsatisfying. It seems to paper over the problem with a philosophical non-answer. The many worlds interpretation, as we encountered in the context of time travel, takes a different approach. There is no collapse. The wave function always evolves according to the Schrödinger equation, branching at every quantum juncture so that every possible outcome is realized somewhere in the vast ramifying tree of parallel worlds. The pilot wave theory, developed by Louis de Broglie and later extended by David Bohm, proposes that particles have definite positions at all times, guided by a real pilot wave that evolves according to the Schrödinger equation. The apparent randomness of quantum measurement is not fundamental, but reflects our ignorance of the particle's precise initial conditions. The relational interpretation, advocated by the physicist Carlo Rovelli, argues that quantum states are not objective properties of systems, but are relational, defined only with respect to some other system. There is no measurement problem because there is no observer-independent reality to collapse. All physical facts are relational facts. Each of these interpretations is mathematically consistent with the observed predictions of quantum mechanics. Each describes a fundamentally different picture of what reality is, and currently, no experiment can distinguish between them, because they all make identical predictions. The question of which interpretation is correct, or whether the question itself is well posed, is one of the most profound and least resolved in all of science. What we can say is this: whichever interpretation is correct, reality at its most fundamental level does not look like the world of everyday objects. It does not look like particles bouncing off each other in empty space. It does not look like anything we have evolved intuitions for, anything we can visualize, anything that resembles the contents of ordinary experience. The bedrock of reality is strange, deeply, irreducibly, perhaps permanently strange. Emergence and the levels of reality. And yet, the coffee mug is still there. Despite all of this, despite the fields and the superpositions and the entanglement and the holographic principle and the measurement problem, the coffee mug sits solidly on the table. It holds coffee. It does not tunnel through the table. It does not spontaneously dissolve into a quantum superposition of mug and not mug. The laws of the everyday world are real and reliable, and we ignore them at our peril. How do we square this? The answer lies in a concept that physicists and philosophers call emergence. Complex systems built from simpler components can exhibit properties and behaviors that are not present in or predictable from the components themselves. Water molecules do not have wetness. Individual neurons do not have thoughts. Atoms of iron do not have ferromagnetism. These properties emerge from the collective behavior of large numbers of simpler parts interacting according to simpler rules. The solid, classical world of everyday objects emerges from the quantum world of fields and superpositions. It is not that quantum mechanics stops applying at some particular scale. It is that the quantum effects, the superpositions, the interference, the entanglement, average out over the enormous numbers of particles in a macroscopic object. The quantum randomness cancels. The classical certainty emerges. This process is called decoherence. When a quantum system interacts with its environment, the air, the light, the thermal radiation constantly streaming through every object, the entanglement between the system and its environment grows rapidly and massively. The different branches of the superposition stop interfering with each other. The system begins to behave classically. The fuzziness of the quantum world resolves at macroscopic scales into the sharp contours of everyday experience. This does not solve the measurement problem. Decoherence explains why we never see macroscopic superpositions, but it does not on its own explain why any particular outcome occurs. The cat still seems to be both alive and dead at the quantum level. Decoherence explains why we never directly see this, but not why we see one definite outcome rather than another. But it does explain why the mug is solid, why the table holds it, why the classical world is, for all practical purposes, trustworthy. Reality has levels. Each level obeys its own laws, which emerge from the level below. Chemistry emerges from physics. Biology emerges from chemistry. The rich, warm, complicated world of human experience emerges from biology. None of these emergent levels is less real for being emergent. The fact that love ultimately involves electrochemical signals in neurons does not make love less real. The fact that the coffee mug is, ultimately, mostly empty space does not make it less solid. Reality is layered, and each layer is genuinely, not merely apparently, real. What we do not know, it is worth being honest about how much of this remains unsettled. We do not have a theory of quantum gravity. The two great frameworks of modern physics, quantum field theory and general relativity, are mutually incompatible at the deepest level, and no successful unification has been achieved. String theory and loop quantum gravity are the leading candidates, but neither has made a confirmed experimental prediction that distinguishes it from existing theories. We do not know what dark matter is. We have abundant evidence for its existence. From the rotation curves of galaxies to the large-scale structure of the cosmic web to the patterns of the cosmic microwave background. But no direct detection has been made, and the identity of the dark matter particle, or particles, remains unknown. We do not understand dark energy. The accelerating expansion of the universe is one of the most robust observational facts in cosmology, established by multiple independent lines of evidence. The energy driving it, sometimes modeled as a cosmological constant, a fixed energy density of empty space, accounts for roughly 68% of the universe's total energy budget. We have no fundamental explanation for its value, which is famously and mysteriously smaller than theoretical predictions by a factor of around 10 to the power of 120. This discrepancy between theory and observation is sometimes called the worst prediction in the history of physics. We do not fully understand why the universe is made of matter rather than antimatter. The Standard Model's explanation for the observed matter-antimatter asymmetry is insufficient by many orders of magnitude. Something happened in the universe's first moments that tilted the balance, and we do not know what. We do not know whether the universe is fundamentally deterministic or genuinely random. Different interpretations of quantum mechanics give different answers to this question, and we currently have no way to tell which is correct. We do not know whether our universe is the only one, or one of infinitely many. The string theory landscape, eternal inflation, and the many worlds interpretation of quantum mechanics all suggest, in different ways, a multiverse of staggering scale. Whether this idea is scientific, whether it is, in principle, testable, is a question on which physicists are sharply divided, and we do not know what, if anything, lies below the quantum fields of the Standard Model. We have peeled back layer after layer, molecules to atoms to nuclei to quarks to fields, and each time we have found a new and deeper description. But is there a bottom? Is there a level at which the question, "What is this made of?" finally has the answer, "Nothing further. This is the ground floor"? Or does the tower of descriptions go on forever, turtles all the way down? We genuinely do not know. The monstrous and the beautiful. Pick up the object again, the coffee mug, the phone, the pen, whatever it was you reached for at the start of this. Look at it differently now. It is made of molecules, bound together by shared electrons dancing in quantum superposition between atomic nuclei. The nuclei are made of protons and neutrons, themselves made of quarks bound by gluons. Tiny storms of color charge, perpetually exchanging the particles that carry the strong force at a speed and intensity that makes the heart of the sun look sedate. The electrons and quarks are excitations in quantum fields that extend across the entire observable universe. Fields that are related by deep mathematical symmetries we have only begun to understand. Fields that exist in space-time whose own geometry is dynamical, mutable, shaped by the matter within it. The apparent solidity of the object, the heft you feel when you hold it, the resistance it offers when you press against it, is not the close packing of little balls of matter. It is the electromagnetic force acting between the quantum fields of the atoms in your hand and the atoms of the object, preventing the two from occupying the same space. The solidity is relational. It is a consequence of the way the fields interact, not an intrinsic property of the matter. And the color of the object, the specific wavelengths of light it reflects into your eyes. That is the quantum mechanics of electrons jumping between energy levels, emitting and absorbing photons according to rules that Niels Bohr and Werner Heisenberg and Paul Dirac spent decades working out. Rules that still, a century later, defy any intuitive explanation but produce predictions of devastating accuracy. What you are holding right now is a brief local arrangement of quantum fields in a particular region of dynamical space-time, maintained in its current form by electrostatic and quantum mechanical forces, perceptible to you only because photons, excitations of the electromagnetic field, are bouncing off it into the light-sensitive cells at the back of your eyes, triggering electrical signals in your neurons that your brain constructs through processes that are themselves deeply mysterious, into the vivid and immediate experience of holding an object in your hand. None of this makes the mug less real, but all of it should make you hesitate just for a moment before treating the word real as though you know what it means. Because the deepest lesson of a century of fundamental physics is that reality, the actual underlying structure of things, the bedrock beneath the bedrock, does not look like the world of our everyday experience. It is not made of little colored balls bouncing in empty space. It is not continuous or solid or sharp or well-defined. It is made of probabilities and fields and superpositions and entanglements and curved geometry, and at the very deepest levels it remains stubbornly, magnificently beyond our full understanding. The question of what reality is made of is not one that physics has finished answering. It is not one that physics has nearly finished answering. Every layer we peel back reveals another layer beneath, stranger and more intricate than the last, and the honest answer to the question, right now, today, with all our accumulated understanding, is that we do not know. We know a very great deal. We have mapped the territory of the quantum world with extraordinary precision. We have built theories that work consistently and reliably from the smallest subatomic scales to the large-scale structure of the cosmos. We have found fields where we expected particles, curvature where we expected force, and probability where we expected certainty. But the ground floor, the level at which the question, "What is this made of?" finally runs out of answer, has not been found. It may not exist. The universe may have no bottom, no final layer, no bedrock. The territory may go all the way down without end. Or it may not. There may be a final theory, a set of equations from which all of physics follows, a description so deep and so unified that no further question of the same type can be asked. The hunt for this theory, the theory of everything, in the physicist's phrase, is one of the great ongoing projects of human thought, pursued by thousands of minds across the world, inching forward year by year through a landscape of mathematics of vertiginous complexity. We do not know if we will find it. We do not know if it exists to be found. But we are looking. And the object in your hand, that unremarkable, completely solid, absolutely real thing, is made of the same stuff as everything else in the universe, held together by the same forces, governed by the same laws, part of the same vast, strange, shimmering fabric. That fabric has been the subject of human inquiry for as long as humans have been capable of inquiry, and it is still giving up its secrets, one at a time. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment. Tell us what you think. Thanks for watching, and we'll see you next time.